Hello, everyone. Welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen, Associate Professor in the Department of Chemistry and Biochemistry at Florida State University. I'm a photochemist/photophysicist. I shine light on molecules and materials and find out where that light energy goes, whether it's moving electrons, making and breaking bonds, moving energy around, and hopefully doing something useful like catalysis, like solar energy conversion. But more importantly, joining me today is Dr. David Collins. David, if you wouldn't mind introducing yourself.
Sure, I'm David Collins. I'm an astrophysicist at sorry, I'm forcing up the mic.
Yep.
I'm an astrophysicist at FSU, and I'm mostly concerned with star formation. I make computer models of stars forming, and one thing I'm really interested in is the fluid dynamics of supersonic flows, which underpins star formation, because we know that that when two big clouds of gas collide in outer space, they collide at speeds that are large compared to the speed of sound in the cloud. So they send a lot of shock waves through the cloud that make the cloud denser, and those density perturbations can form stars, or they break up density perturbations and they keep the cloud supported from globally collapsing. So it's a complex dance of violent fluid dynamics.
What do you typically teach at FSU?
Right now I'm teaching a fluid dynamics class, which is basically Navier-Stokes equation, and it's about understanding how fluids flow and turbulence.
Awesome. Equally important, what game are we playing tonight?
So tonight we're going to play a little bit of Mario Kart, and then probably a little bit of Zelda.
All right. Let's do it.
And
So we
let's
have
get started.
A Switch hooked up to the big screen, ladies and gentlemen. So we're going to play some
Start
Mario
back at the
Kart
beginning so everybody knows where we are.
while we're answering science questions. So anyone joining us on Twitch right now, you can't see this, but we are live from inside the IMAX Theater in the Challenger Center in Tallahassee. And so we have transplanted the entire streaming setup to this particular location. And now we are streaming live across that screen. And so you can see the labels there so people can see it live. But yeah, exciting. I even have an IMAX. You can see right there the infinite regression prediction. You can see a shot of the screen. But yeah, David, let's do this. Dive right in.
Play.
Settle in. We'll get some.
Let's play one I like.
All right. Yeah, no pressure. You're in front of an audience on how big is that? 50 feet across?
I know, right?
The biggest screen in Tallahassee. We're currently streaming on live in Challenger Center, which is pretty exciting.
Everybody can see how bad I am at Mario Kart.
And this is one of those things where it's like, hey, do you want to do Ask a Scientist Gaming in the big screen IMAX
Yes,
theater?
I do.
You say yes. You say yes every single time. But yeah, we'll let David settle in a little bit before we grill him with some questions.
Yeah.
So when was the last time you played Mario Kart?
A couple of days ago.
Okay, that's not bad.
No. And I'm playing on 100, so it shouldn't be too bad.
Well, key to our stream is mediocre gameplay.
That's
so
right.
as long as you live up to that.
King of mediocre gameplay.
Oh, perfect. So this is still the most recent Mario Kart. There hasn't been a release after this one, right?
I don't think so. They went with the DLC route, so they released a whole. So the game originally came with eight courses, and they released another 8. If you sign up for their exorbitant streaming subscription service.
They've announced the Switch 2 at some point. So
really?
Yeah.
What have they said? I haven't actually.
It'll be backwards compatible at the very least, so
That's
all our
great.
games will go forward. But
Because you know what, man, I'm pretty invested in our Animal Crossing island.
Yeah. I don't know if you haven't. It's a Switch account for that, right?
Right.
Yeah. So it should translate, but we'll see.
One would hope.
All right, you've had 30 seconds to settle into gameplay.
Okay,
so
fantastic.
we'll start with our classic question we ask every single guest.
Okay,
and this
cool.
is important because a lot of people out there think scientists were just born to do science, right? We knew from day one this is what our careers were going to be.
Oh, yeah.
Presumably, 6-year-old David Collins was not sitting around saying, I'm going to be in an IMAX theater playing Super Mario Kart while talking about astrophysics. Instead, there were key points along the way, key events that you decided, I want to do sciences in a particular flavor of science, which is physics. And of physics, I want to do the subset of astrophysics. And
Right.
so what were the key events you remember along the way that made you transition from 6-year-old David to where you are sitting right now?
Well, oh, God, no, no, go. Okay, I won. Sorry. I was born. Sorry, I got nowhere funny to go with that. So I started off my kind of adultish life as a musician. So when I was in high school, I got good at playing the tuba, and so I thought I'd do that. So I got really good at doing that. And then I went to music school for it, and I realized after a year of that I did not want the grind of being a professional musician. I wasn't as clear as I am now about why I needed to leave. But really, one thing that I tell my students all the time is you need to find a job where you want the grind, where the sucky parts outweigh are outweighed by why you're doing it in the first place. So especially, a lot of people want to do astronomy. Well, astronomy is very exciting because, what's more exciting than the creation of the universe? But if you don't want to actually do a buttload of math, then it's really not for you. In this particular route, not to be dismissive of all particular career paths. But so being a professional musician, I don't think was really for me because it's for a variety of reasons. At the time, I really knew that I didn't want to teach high school band, which I could see was actually my most probable actual job, because I didn't know how to deal with students like myself. Oh, my mom is calling me. I love that. So I'm gonna have to call her back.
Oh, did you just deter a red shell with a banana peel?
Oh, yeah.
If so, that's amazing. Well done.
Oh yeah, you hang them out your butt.
I like it.
It's the butter. So anyway, so I didn't really want the grind of being a musician. I didn't want to be a band teacher because I didn't know, and really at the time, I didn't have any idea how to be a band teacher for somebody like me because I didn't know how to be somebody like me. It was kind of a ridiculous proposition to even, it's like an existential problem. So anyway, so I went to study engineering at the University of Cincinnati because it's a good school and they've got a good track record of getting you a job, and I needed to do more math in my life. And cutting out a little bit, for an extra one class, you get a physics minor when you're an engineering student. So I decided that I was going to take quantum mechanics because that sounded like great fun.
Said no one ever except you.
Right. And I went to that class, and I can remember large fractions of that class really clearly, more than I think any other single class that I've been to. And I didn't understand a single thing that was going on. Like, he was talking about Maxwell's equations and scattering, and I was like, well, I have to go change my major and take all those classes so that I come back and take this, because why can't I do that? That sounds really cool. And rolling back, like, I was a little bit nerdy when I was a kid. When I was in 7th grade, there was this huge poster on the wall of all of the particles that were known at the time, and at that time, not all the quarks had been discovered. So that was so it was a very tantalizing and exciting thing that there was, like, you could know all of the things, like you could know everything about all of the particles. Kind of hung over my little 7th grade mind, and that was very, very intriguing. And that always kind of stuck with me even through everything else. So by the time I got to quantum mechanics, those ideas had been ruminating for a little while.
Do you remember back to the list of particles on that? Like, do you still remember that? How off it was?
I mean, it was basically the standard model as we know it now.
Okay.
It was pretty well understood at the time. It
Yeah.
just they hadn't discovered the top or one of the other ones. The top didn't come till I was in college.
And George Jettison would like to interject here. You were a lot nerdy.
Yeah, that's not wrong.
Is that your brother?
That, in fact, is.
George, welcome back to the stream. Thank you for joining us. Feel free to drop any lines you'd like to about David. Your comments are actually projected on the IMAX screen right now, so feel free to comment accordingly. Sorry for that.
No worries. Butter. So I changed my major and wound up doing pretty good, and went to grad school and thought I was going to do particle physics, and then really didn't gel with particle physics at the time. Part of the reason was this was the early 2000s was when I was starting grad school, and the LHC hadn't turned on yet. Like it was still a decade away from taking light and really discovering anything.
LHC being Large Hadron Collider.
The Large Hadron Collider, yeah, which is the largest machine ever built. It's a very exciting object, but that didn't seem super fun. But making computer models did, and I thought that I would get a job with the computational physics group, who made computer models of galaxies forming. In part because my buddy Brian was in that group, and I really enjoyed hanging around with him, and I thought that would be pretty fun to continue running straight into that tree. Okay, get one of those. Yeah, there you go. And I'm gonna get that guy too. There you go. Thank you. Anyway, so I joined the computational astrophysics group because I had no idea if astrophysics was actually going to work out and I was going to be able to get a job doing physics. But I figured if I could learn how to program big computers, that would get me a job of all kinds. So then physics wound up working out. Long story short. Are there more interesting questions too?
Cuddle Puppy coming in strong. Speaking of star formations, what do you think about Chapel Roan?
Who's Chapel Roan?
That sounds about right. She is a singer that has meteoric rise to fame. So okay. Star formation, get it?
I understand.
Thank you, Cuddle Puppy. Always interjecting with the good questions. Anyway, how'd you land at FSU?
I was looking for a job, and so I applied to kind of everything that sounded even remotely right. I really didn't think that I was going to get this job because really the people who were here did supernova. And that continues to be the case. We're really a supernova group. Which is a great thing. Like, it's great to have so many people who are experts in one thing in various kinds. So you really get a good complete picture of how things work. So I didn't think that I was going to get the job, but I guess everything went pretty well. And here I am, because I do mostly, at the time I was doing exclusively star formation. Since then I've started doing some more work on things like CMB foregrounds, and I've started a couple of experimental campaigns also to study astrophysics. Sorry, I totally trailed off because I ran into that truck.
Dave, you're being asked to talk louder.
Oh, talk louder. Into which mic should I talk louder?
Yeah, both of them, it's fine.
Both of them? All right.
There you go.
All right, I'll fill the room. All right. Did I answer that question?
Yeah, you did. So anyone that's just coming to Ask a Scientist Gaming for the first time, I want to convey how difficult it is to play video games while answering complex questions. Even casual questions, if you're not used to talking regularly while video gaming, it is a challenge. But that's one of the reasons I love doing this stream, is because there's nothing more humanizing and knocks you off your ivory tower than sucking at a video game while trying to talk science. So welcome to Ask a Scientist Gaming, and thank you for joining us. If anyone in the theater has questions, you can feel free to come up to the stream and ask them, and we'll be happy to answer those. But yeah, if you guys have questions in chat, put them in there. But yeah, we're going to talk astrophysics or color chemistry, photochemistry, whatever. If you guys have questions, we're happy to answer them.
Or really anything else. When I was a little kid, my dad had a bet with my mom. No, before I was born, my dad had a bet with my mom that she couldn't get him to say "I don't know" 10 times, which says wonders about both of them. I love them so much. Don't read too deep into that, or you'll get it right. So one of the things that I learned from my dad was how to BS answers on the fly using your existing knowledge, which has served me incredibly well, because that's really what I do for a living. I come up with a problem, and my job is to BS some kind of solution until I get it right, and then iterate. See if I'm right. I'm usually not the first couple of times, but
Your students are listening. That's what candidacy exam is.
That's right.
Hey, you did it.
Yay. Oh, did I? Oh, how many stars did I get? I forgot to look.
3 stars.
Oh, yay.
So that's not bad. That's a good start. So
That's why I'm playing on 100, because I can do that.
before the official stream, we had to spend some time just playing on the monster IMAX theater screen. So
It was delightful.
yeah,
How many people are in the theater?
I have no idea. I can't see beyond these lights. The answer is at least 3,
Oh, can I move this mic closer?
potentially.
I can optimize that a little better. All right.
Yeah, we've been negotiating the complexities of having both video, game audio, and our voice audio, both going to the IMAX theater and to the Twitch stream, and it's been a battle, but hopefully it works out. Cuddle puppy. Who's going to be the next big thing in Hollywood? Why are you asking entertainment questions? He has no idea.
Yeah, that's really not wrong. That's one thing that I've found. They haven't really figured out how to advertise movies to me. I've largely cut a lot of cords, and Facebook was really terrible at advertising anything interesting to me, and then I cut them out.
Yeah.
So I never see information about what's good on the big screen anymore. So I'm kind of cut off from that.
Yeah, that's fair. But you are an expert on star formation.
That's right.
Puppy
That's
has
right.
pointed out, so.
That's accurate. I am a little distracted, so I might miss some hilarious jokes. It brings out the best in me.
That's Stag, one of our guests for the stream. Scott, welcome. Thank you for joining us in
Oh, great.
person
Hi.
in this audience, but chatting as well. So dual purpose here. But he wants to know, what do you think the next big splashy experimental result in astrophysics will be? So everything the Webb telescope takes in is a new something.
Yeah, so Webb has just been exciting and continues to be exciting. So star formation happens earlier and weirder and not really in galaxies in the same way that we thought it should. So Webb is just a gold mine of exciting new results. I think that in terms of really unlocking the last couple of pieces of things like the standard model. So the standard model is this really remarkable theoretical model of how all of the particles in the universe work together. And it's remarkably successful, except for a couple of glaring holes. And I think that probably the next breakthroughs, like the next really fundamental breakthroughs, are probably coming in neutrinos, which are going to answer some of those questions. Some of the questions about, about neutrinos themselves and about what mass really means. Because neutrinos have some kind of mass, but they don't couple to the Higgs, so why do they have a mass? But we know they have to. So I think that there's a lot of energy being put into high-quality neutrino production and high-quality neutrino experiments. So I think that's my money for the next really kind of earth-shattering or like foundational, probably not going to be earth-shattering at this point, but it's going to be foundational changes.
I mean, so a related question. So Nobel Prize was this week. We won't dive into that necessarily right away, but what's the next Nobel Prize in astrophysics going to be?
Well, CMB mode, B modes in the CMB is the next clear contender. So that one's my favorite because I am working on that, though I'm not anywhere near the actual results. So
can you translate that
yes, I
acronym
can.
soup to the general audience?
So, so the cosmic microwave background is the leftover light from the birth of the universe. The universe was born in a big homogeneous soup that was very hot, and it got colder with time. And at some point in time, it got cold enough to form atomic hydrogen. So the first time that hydrogen was formed, and then the universe got very, very transparent. A photon can't go very far in a plasma because a photon bounces off of the protons and the electrons like crazy. But as soon as the universe was basically neutral, then photons could travel. And so and now those photons that were 14 billion degrees in the early universe are only 3 Kelvin, so they're very cold. They're very long photons, but we can measure them. And one of the things that we can measure are an imprint of the sound waves that were rattling around in the early universe. Because after this, they call it the surface of last scattering, which is when all of the hydrogen became atomic, and photons could travel freely, and you could actually see through the universe. There were spots that were hotter and spots that were colder because of sound waves that were traveling around in the plasma. And from those sound waves, you can learn. We've learned an enormous amount about the content of. Oh, that was Lab 3. Don't stop playing. So from the cosmic microwave background, we've learned an enormous amount. So there are a lot of telescopes. So one Nobel Prize in astrophysics went to the discovery of the CMB. One Nobel Prize went to the discovery that the CMB is a black body, and what that means is that the universe looks like a big oven, and not a very hot oven, but a big oven. And that was Penzias and Wilson in '65, I think. I think the next Nobel Prize that's going to come for the CMB is going to be in its polarization. So the signal is in this surface of last scattering is polarized because I should probably talk about polarization. So polarization is when all of the photons line up in one direction. So like you can get polarized sunglasses to go out fishing, which block the glare off the surface of the water, because the photons are all reflected off the surface of the water. They all happen to line up in a certain direction. So you get a polarized sunglasses that only let through photons that are polarized in the other direction, and you can block the photons that are coming off the surface of the lake, and you can see the fish. So polarization is a pretty common phenomena, and it happens in the early universe for a couple of reasons. And one of those reasons is gravitational waves from the Big Bang. So the cosmic microwave background is the earliest that we can see. It happened about 400,000 years after the birth of the universe. And that's as old as we can see. But if we could see gravitational waves from the birth of the universe itself that are imprinted on the cosmic microwave background, then we can see back towards the actual beginning of time, which would be really exciting, because there's a lot of questions that we have about the birth of the universe. So by measuring the polarization of the cosmic microwave background, we can measure properties of how the universe was born. And that is certainly, once it's discovered, and there's an enormous amount of time and energy, someone is winning the Nobel Prize. And there are several people, and I'm probably should be able to pinpoint exactly who is responsible off the top of my head, but I'm getting hit by this blue shell. But so that might not be, oh, you can blow up the train? That was cool. I can't blow up that red shell because I got nobody. But that's a slam dunk Nobel Prize in astronomy is when people actually measure B modes, and it'll probably go to the team that actually does it, and whoever they determine is really responsible for predicting them, which I think is probably a number of people, but
they'll narrow it down to 3.
They'll narrow it down to 3. So
if I'm remembering correctly, there was an early story about the microwave background. They thought it was like pigeon poop on the dish or something like that.
Oh yeah.
They had to control for it not being.
Well, it was like originally the first thing that they found was a pigeon's nest in the antenna, and it was causing problems.
I see.
So that was the first thing they actually had to tackle.
I mean, it's such an interesting problem because you have to show that the noise is real. Like,
right.
Usually you're trying to get signal out of the noise. This is trying to show the noise is real.
Right. It's trying to and it's showing that the noise is uniform.
Yeah.
And everywhere, and not coming from the planet, and you're not crazy, and just making it up with some hot wire somewhere in your setup.
Fair. So Cuddle Puppy has a suggestion for the next Nobel Prize in astrophysics. Will be for the person who makes sound work in space, so we can have sick X-wing and TIE fighter battles.
Sound does work in space.
Does it?
Yeah. Sound works in space all the time. Remember how I was talking about clouds collide faster than the speed of sound in that cloud? Yeah. That's because there's sound in that cloud. There's lots of sound in outer space. You're just not impedance matched to hear it. So if you ever have dealt with hydrophones underwater, so a hydrophone does not a good job in measuring air because it's not impedance matched. It's not ready for the density of air. It wants something that's much higher density. But it's great for measuring sound underwater. Similarly, a regular microphone like this SM58 that in front of me is great for measuring sound, but would do a bad job underwater because the water's too heavy for what it's used to. So sound in outer space is just very low density, and your ears are not designed to handle it. Now, if you had an ear the size of the moon, then you would be impedance matched to hear sound in space. But you do not.
All right, so the answer is they can hear you scream in space. You just need a big enough ear.
Yeah, it's just you just don't couple to it very well. So it's a lot like how like a grand piano works. So if you think about a grand piano is a lot of steel strings that make a sound and a huge piece of wood. And if you just played steel strings, you wouldn't hear very much. You need to couple to the air with the soundboard, because the soundboard is big and wide and not very heavy, whereas the strings are small and tiny and very heavy. So you need to couple to the air, which is big and low density, using the soundboard.
All right, catching up on a couple things. MJD820, thank you for the follow. Thank you for joining us. If you guys are watching and not follow, click the follow button. It helps us with viewer numbers and gets our visibility up.
Oh, hi,
also, you get some standard internet units. We'll probably do some predictions later in the night, but for now, we're going to hang out and play a little bit. Contra Acrostics, thank you for the subscription. Thank you for joining us again. It's always a pleasure to have you on stream. Yeah, you help us with our drinking habit, although we're not drinking tonight because we're in the Challenger Center. But thank you. You're buying a beer for me and my guests, so we really appreciate it. So thank you for this subscription. Luca, welcome to the stream. First time chat. Thank you for joining us. Luca has a question. What do you think are some of the most common misconceptions about astrophysics? What does general populace get wrong? And not just can you hear a scream in space?
Well, that's a pretty common one. So that's but even I don't know. Everybody's going to get that wrong because most people don't think about space as a fluid. I do because that's what I do because it is. Well, so one question that I get all the time. So that's a super interesting question. I should probably spend a minute and write some of those down so I have them in my pocket.
I mean, make a good book.
Right.
Like
it would.
Each chapter be a misconception and you debunk it with the science.
Right. So one question that I get a lot is, what is space expanding into? And that's something that people have a hard time with because that is, I would say that that's a very common misconception. People don't really have a good conception of the expanding universe and what that actually means. And part of the reason is that people have a hard time with infinity and people have a hard time with space being infinite. Because it's not expanding into anything. Oh, I really wanted that mushroom. It's not expanding into anything because it's all infinite. There's more space out there. And so because we've assumed that it's infinite, and we can actually measure that it's infinite. So we can measure. So if you look out with the best telescope that you can at the earliest photons that you can, then you can see out to what's called the causal horizon, which is the size of the known universe. And that's basically as far as a photon can go in the universe. So, but beyond that, nothing can ever have connected with itself. And we can tell by our observations of this cosmic microwave background and some other things that the universe that we live in is at least 200 times larger than the causal horizon that we live in. And that is something that a lot of people have a hard time understanding because it takes a minute to think about, well, okay, if I look out and I look back in time and I look back 13 billion years, then I'll see the beginning of the universe and it's 13 billion years away, which is about right. And that's the edge of the universe. But if I go 14 billion years to the east, then I'll see the same thing. Or if I go 20 billion years in any direction, or light years in any direction, then I'll see the same thing.
I mean, so the corollary misunderstanding or question might be what happened before the Big Bang?
Yeah. Everybody hates my answer.
Let's do it.
There's nothing before the Big Bang. It doesn't make any sense as a question. That's when time starts. There is no before. That's the start of time.
I mean, that's the inverse of infinity.
That's
absolute
people have a
zero.
very hard time with that. And I did too for a long time. And then I realized, well, I mean, either your choice is it starts at some time or it goes back to t equals minus infinity. And I also have a problem with that. Because that doesn't make any sense to me. Or it has to start somewhere. Those are the only two options. There's no in between. It doesn't make any sense otherwise.
Astro D-Nerd, thank you for the follow. Thank you for joining us on Ask a Scientist Gaming. Red the Mumbler, thank you for joining us. Well, thank you for the first time chat. Red the Mumbler wants to know, what would happen to the solar system if one of those giant high-speed gas clouds crashed into it? Also note, it is not a fart joke.
Hey, what's up,
they had to clarify.
Nothing, because as I was saying before, it's about the impedance. So the solar system is actually very small and dense. So if one of these big clouds went through, not a lot would happen. We would see, because we have a very intricate relationship with the ionosphere and the electrons and the magnetosphere around our planet, because we have all these satellites in it, we would certainly be able to measure it. It wouldn't cause a mass extinction because we're so small. It would just kind of pass through. Oh yeah, I should play again.
So these dense clouds are not really dense at all.
Yeah. That's the funny thing is they're dense for outer space, which is really not very dense. So they're 100 particles per cubic centimeter.
I mean, I love that. So I've sat on a committee for one of David's students before, and so I do like, ultra fast spectroscopy, which is femtosecond measurements. And Dave's student said the line, I don't know what it was. It was a young star.
Oh yeah,
And like,
young
what
star.
does young mean in the world of astrophysics and time scale of? We talk on very different scales.
Right, 100,000 years is young.
Yeah,
It's a very young object.
just a baby.
Right.
All right. Contracrostics wants to know, could dark matter just be black holes all around the place?
Yes. Maybe. Probably not. They went and looked and measured it and can pretty definitively say that there aren't. So the cool measurement that they did was called microlensing. If you just park a telescope at a field of stars and there are little tiny black holes, then ever so often, because there's really a lot of stars in the galaxy, ever so often a black hole will go in front of it and it will act like a little lens and make that star a little brighter. And you can measure this, and they did a nice job. And they measured more things than they were expecting, but only enough to make up for about 10% of the dark matter that we need. So that's a very good idea, and we went and looked, and probably not. So to the best of our measurements. And that only, so dark matter, let me give you my very short lecture on dark matter. So there are probably 5 things that we have measured that are wrong. So, for instance, the first place we really noticed a problem is in the velocity in huge clusters of galaxies. So the first place anybody noticed something that turned out to be what we now call dark matter, was Fritz Zwicky in the 30s. And he said, okay, there's this huge cluster of galaxies. There's 1,000 galaxies here, and they're whipping around at 1,000 kilometers a second. And if they were actually doing that, given where they are and how fast it looks like they're going, and if they were just going to fly off into space, this thing would only last for 1 million years, and it would go away. So why does this object exist? It shouldn't exist. These things are moving too fast. So maybe it's viscosity. He called it viscosity, which doesn't work because these are very, very low density plasmas. But he didn't understand. So then the next place that they saw dark matter as a problem was in galaxy rotation. So if you look at a single galaxy, they're all rotating too fast. They should fly apart, but they don't. They're rotating very quickly. And so that was a puzzle. But then also back to this cosmic microwave background, which really is one of the most useful things. That, because it's this, it's kind of like listening to a trumpet and understanding that it's a trumpet and not a xylophone. If you listen to the spectrum of it, you can tell what's going on inside. And one of the things that it tells you is how much pressureless matter there is, and that's matter that has no pressure. And in the early universe, that's a thing that we don't understand. So it exists with gravity, but not with any of the repulsive forces that would come with existing. So there's this signal in the CMB, and there are 5 or 6 other things that all point to there has to be some kind of particle that we haven't found yet. It's probably not that the equations are wrong. It's probably a particle that we haven't found. But both things exist. So we have a problem, and sometimes in nature, the problem is solved by a particle that we're missing. And sometimes in nature, it's that we didn't understand the equations properly. This time, I think we're not going to make these equations work.
So you think it is a particle?
I'm pretty sure it's a particle.
Is there a hypothesis on how to make this particle?
There are, and the stories change, and this story has changed since I started here. But when I started, the story was supersymmetry. So in this standard model that I was talking about before, this is a great model that talks about how particles exist and why they exist and why there are so many of them. But you can write it down like with a couple of minus signs in the right spot, and you get bizarro world particles that they call supersymmetry, and there's a nice symmetry to all of the particles that exist. So we have things like electrons, and those go to things like protons, and things like protons go to things like electrons, and things that were small get big, and things that were big get small. It's a very cute thing, and everybody thought it was right for the longest time, and nobody really talks about that. Well, I mean, people talk about that, but it hasn't shown up. Like, we think we would have seen it at this point. So we think the LHC would have seen something, but it hasn't seen anything there. We think we would have seen something in like CMB non-Gaussianities or something like that, but we haven't seen anything there. So there are, so it's probably a particle. If it was math, we probably would have seen it.
And that particle is worth a Nobel Prize, presumably.
Yes.
Whoever views that.
At least one.
All right, Opie, thank you for the follow. Luco, thank you for the follow. Thank you for joining us at Ask a Scientist Gaming, live from the Challenger Center in Tallahassee. Opie has a question. Do wormholes act like they do in Interstellar?
Well, wormholes, okay. I don't believe the wormholes are real. So a wormhole is basically unstable. In principle, if a wormhole exists, you've got a black hole on one side and something that comes out on the other side, which would be some kind of white hole. But we know that wormholes are unstable, so I don't think that one could form naturally. So if it did exist, it would be some other kind of intentional construction.
So Cuddle Puppy has an existential comment about Mario Kart. I like how Mario Kart being in first place means you're a magnet for violence.
Oh yeah, that's wrong. Or that's not wrong.
Phenomenologically, it's called rubber banding, and it's built into the game.
Yeah,
so
it's pretty great.
Equilibrate skill sets. So it's great for kids. They love playing this. I think you can turn it off, actually. In certain gameplay modes, you can.
Oh yeah, we want to see something fun? I'll show you. It's more fun if you were playing.
Yeah.
But you can turn it on so that it's all blue shells. So the blue shell, if you haven't played this game, the blue shell seeks out the person in first and blows them up. So if everybody only gets blue shells all of the time, it's a complete cluster fart.
It's ultra violence.
It's ultra violent. Like there's a race to not be in first place because you get blown up. But if you're in second place, you're probably going to get blown up anyway. It's outstanding fun.
I did not know that. I'll have to try that.
Yeah, it's really fun.
All right. Scott Stack wants to know, what's your favorite paper that you have published and why?
Oh, my favorite paper that I have
Careful, your
published.
students might be listening.
The problem with papers is I know that they're ready to publish when I am sick of them.
So you hate every paper that's published.
I'm done with all of them when they're done. I'm like, okay, we move on. But I'm actually pretty happy with, I don't know. If I just had to pick one, probably my code method paper, because I feel like that helped move people forward in doing computational astrophysics.
So this is a paper as a PI at FSU?
No, this was the paper that was my my thesis work. Really.
Oh wow.
And it's basically a description of how I made this code work, which is it's tricky business to make magnetic fields work in code. They have this vector field nest that won't go away, and vector fields are kind of a headache. Into the lava I go.
But you survived, so physics be damned.
That's right. And that makes things tricky. I'll cut the jargon out. But we were able to make that work pretty well. And then a lot of people read that paper, but I'm pretty happy with the papers that Branyo and I got out. Mostly because they were all his ideas. and that was really satisfying. And they're fun papers. And I'm happy with this this cosmic microwave background paper that I got out. So we got out a paper talking about what the polarization effects of these clouds of gas are. So what do these clouds of gas look like if you're looking for this cosmic microwave background polarization? These clouds of gas are in the way. So we did a study on what, I'm going to blow myself up with that bomb. So we did a study of what big clouds of plasma look like. And it was pretty successful, I think, and I think it'll be pretty useful. I don't know. Maybe my favorite paper is my first recent paper on star formation, because I did something that nobody else has really done, and I think it showed things that are pretty interesting about how stars come to be. Everything's a fractal.
The correct answer was you love all your papers equally, and you cannot choose between them.
That's right. It's some kind of Sophie's choice.
Exactly. All right. Opie wants to know, considering we don't technically know how black holes form, do you have a personal opinion, and how do you think they form?
Oh, well, so I think that Type 2 supernova is certainly a way that they do. I think that there's no way for that to not be a way for black holes to form. Because you just have so much stuff, and eventually gravity wins. And gravity, we understand how gravity works pretty well, and we understand how fluid dynamics works pretty well. And we understand things like white dwarfs and neutron stars, and so, and those all exist and we can see real well. And the black holes we do have, we feel like we understand reasonably well. But I don't think that that's the only formation channel of black holes. So I would say that there are really kind of two, at least, sizes of black holes. There are little black holes and really, really goddamn huge black holes. Some of these really goddamn huge black holes are at the centers of galaxies, and we can see them because they're feeding so monstrously. We can see them clear across the universe at the beginning of time. And we don't really understand how they got so huge so fast and why they exist so early. And James Webb is making that just so much harder because it's seeing huge things really early. So we certainly don't know where all of them came from. So I think that there's probably some combination of interesting fluid dynamics properties that allow gas to get out of the way really fast that we don't understand, and something that we don't actually understand. I think that there's some mystery yet that nobody's actually come across.
I mean, so related to that, so Webb has broken a lot of physics, right? It's shown things that we haven't expected. What's the most shocking thing it's seen that we can't explain? Most
shocking. I think these early galaxies are really exciting. I think that's my favorite thing, because they're, and this is really what it was built to do, was to look for things like early galaxies, among other things. Like, it had a lot of things in mind. But because it can see long wavelengths, then it can see high redshifted stuff. So it can see things that are early in the universe. And these galaxies are really misshapen, and they let me roll back for 1 second. So one of the great successes of computers in physics is our understanding of the basic material that the universe is made of, and we call that lambda CDM. And oops,
that was close.
Yeah. And this is basically, so what they did was they said, okay, I can see where all the galaxies are in the sky. And they're kind of clumped together in this foam. It's kind of patchy and it's a fractal. And so if we can predict what that is, starting from what I know the Big Bang looked like, then we think we have a good basic idea of what's in the universe. So there's basically three things. There's dark matter, which we talked about. There's dark energy, which we haven't talked about. And dark energy there's a lot more of it than there is dark matter, and it's a lot weirder and we understand less. And we'll talk about it. We understand it less and less the more we understand it. So we'll talk about that in a second, but there's a buttload of it. And then there's baryons that are like protons and neutrons and stuff that makes us.
Hey David, can I put a shameless plug in for Dark Universe now playing in the Fog Planetarium? The Challenger Learning Center of Tallahassee.
We should watch
Neil deGrasse Tyson's own show. No, which is where I learned about dark energy and dark matter.
Oh, very cool.
That's awesome.
So, shameless plug for Dark Universe at the Fog Planetarium, which I really want to see. It sounds like it's a really dope planetarium.
Yeah,
I'm really
new projectors.
Yeah.
Auto-correcting for seams. Yeah,
that's
I know. Alan told me all about it. It sounds amazing.
Oh, that's very cool.
Yeah.
Okay. Where was I?
I don't know.
I was several stacks deep.
Yeah, you were. You were journeying.
And I hold the whole thing together. Somebody on the stream remind me where I was at.
Man,
Dark energy and then
Oh yeah. Okay, so
well, it started with broken. What web has broken?
right. So okay, why do the weird galaxies look weird? What do we think the galaxies ought to have looked like? That's the next question. Like, if I look at something, I think it looks weird, then I should have some opinion of what it should look like. And that's where I was going with. Why do we think they look weird? We think they look weird because we have these really outstanding computer simulations that are doing a great job of predicting what the structures of the universe look like. And this is, I think, a great success of computer simulations in the I think in the 90s and the early 2000s. And they really kind of nailed down this lambda CDM as the hallmark, which is about 70% weird ass dark energy, about 30% or about 25% dark matter, and about 5% normal baryons. So these computer simulations, they all predict that that tiny little basically round things kind of smash together and form larger things. And the things that what we're actually seeing are much more misshapen than what the computer simulations would show, and they're much and the star formation is nearly as condensed, and so it's not clear. Going back to this black hole question, it's not clear if the galaxies form first or the black holes form first. And if you believe that all black holes come from stars, then clearly the galaxies have to form first, or at least the star has to form first, but the galaxies coming shortly thereafter. But it's possible that there's some other mechanism that we don't understand. And there are probably people who do understand some of the ideas that could exist, but those are ideas that could exist. We don't really have a great understanding of other ways to make black holes because we barely understand them in the first place.
That's fair. All right, Stag wants to know, do you ever get time on the web to test some of your hypotheses? Like, do you ever get to point it somewhere and get some data?
I don't, because that's not a thing that I do, but there are colleagues that I have who do. And web proposals are due this week, so all my friends are freaking out. Especially with a storm coming up.
Well, for the tax-paying viewership, right? This is a project out of NASA. They send this telescope up into space, and you're not just pointing it anywhere at random. There's choices to be made. Space is big, and you have to decide where to point it. And so, what's the process of that? You apply, and then you have to get time on the telescope. How does that work?
That's right. So you get 4 pages, I think. It's really not very much, and you have to describe what camera you're going to use, how long you're going to use it, what you're going to use it for, how you're calibrating it, how many seconds you need, and all of those things. And they're well oversubscribed, and I got eaten by that piranha plant. And then they make some map about where to point the telescope when, because it doesn't move for free, so they need to have a good plan about where it's pointing when. And not everything is visible because the sun's in the way. So proposals go in, and they decide who's getting what, and then you get your time. And then the data shows up sometime later.
So you don't pay for that time.
No, that's correct. You get paid for it. So there's money that's associated with web time, and JW and HST time.
And if you had to put an estimate, so if I want to go to FSU Department of Chemistry and use the ultra fast transient absorption spectrometer, I pay about $15 an hour to use it. If you had to put a number on what it costs to use Webb for an hour.
I think that exists, and I don't know it off the top of my head.
Yeah, order of magnitude. Could you throw a guess in there?
Between $1 and $1 million. Probably closer.
Shameless plug for Deep Sky, now playing in IMAX at the Challenger 30.
Oh yeah.
The James Webb Space Telescope film.
Yeah. It was. Yeah. And that is a great film. It's very fun.
You don't want to put a number on that. I mean,
yeah, I don't remember.
It's over $10,000 an hour.
It's over $10,000 an hour.
Yeah.
I'd say that pretty handy.
All right, catching up on a few other questions. Red the Mumbler wants to know, since you can see them from across the universe, what do those giant black holes at the center of galaxies look like?
Well, you can only they look. So what you get to see is the spectrum from basically one point of light. So you don't get any image of the object. You get a very detailed color of one pixel, if that makes sense. But what you see is an object that takes up only one pixel, no matter how great your camera is, and outshines any galaxy you can find. And they're very blue and very bright, and they're very bright in the X-ray. So they're single, very small points of light, but so ungodly bright that it has to be the source of ultraviolence, of ripping the Jesus out of atoms in the accretion disk around the black hole.
All right.
I can go down that rabbit hole pretty deep if you want. There's another question I can go back to.
There is another question. So Typo wants to know, do parallel universes exist?
There would need to be some other way for our universe and some other universe to be connected if a parallel universe exists in the way that you're thinking. So my boring answer is no, probably not, because we would need some way to bridge them, and we've done pretty substantial measurements about extra dimensions, and we can rule them out pretty handily. That also being said, there's a whole buttload of things that we don't know, so I don't know, maybe.
The answer is maybe. I love it. Science fiction can be right sometimes.
Yeah, that's right. So I mean, I'm certainly not the one to say that we've seen everything.
I like it. All right. Man, we're an hour in, so anyone just joining us, Ask a Scientist Gaming, mediocre gameplay expert, science. I'm Ken Hansen, associate professor in the Department of Chemistry and Biochemistry at Florida State University. I do photochemistry/photophysics, but joining me today is Dr. David Collins, who's an astrophysicist who models star formations and things like that. If you guys have any questions, anything related to astrophysics, or we could talk solar cells, we could talk light matter interactions. But yeah, we're happy to answer your questions as you have them, and I'll walk around the theater at some point and see if other people have any questions. But we have one. Sarah Sumo has a question. First time chat. Thank you for joining us, Sarah. Thank you for joining us for a special stream live from the IMAX Theater and Challenger Center in Tallahassee. Question from Sarah is, what made you get into astrophysics/stars? I'm taking your physics class next semester and I'm excited. Well,
Oh, really? Cool.
First question is, should she be excited?
I hope so. It's my first time teaching that one.
All right.
But
So
I've
mixed
been teaching for
emotions.
about 10 years, so I think it'll be good. Well, so it was kind of a mix of things. So I really wanted to. So I saw this talk by, I'm pretty sure it was Mike Brown at Caltech about exoplanets, and this is before Kepler. This is when there were 2 exoplanets. This is like 2002. So we're really not seeing very many planets. And I thought that it would be fun to make computer models of planets forming because I figured that would be a hot field. And so I went to my advisor, who was not my advisor at the time. He was, and I said, hey, I would like to work for you, and I think I would like to make planets. And he was like, I have no idea how to do that, but I'll let you try it. Which has been a running theme in my life is I have absolutely no idea how hard things are, and I'm really bad at assessing, which gets me in over my head, and then I have to figure it out, which ultimately works out pretty well. Because now my figure it out skills are strong. That was a little rambly because I'm trying to play this video game. But I studied planet formation for a little while, and I studied the code that we were using. After a little while, it became clear to both of us that was maybe not the best use of everybody's time, and we had happened to hire another guy who did star formation, and Mike was like, well, let's all work together. So I got into star formation that way, which is like planet formation. And then planet formation just blew up, and so I'm kind of glad I'm not in that field because the competition is really stiff.
That's fair. Speaking of which, this relates to one of our predictions. And so those of you guys not familiar with Twitch has a feature called predictions. And usually you pop up a question for the audience in the chat to answer, where it's something like, will David win this race? Yes or no? What will be the next bad guy that shows up? So on and so forth. But on Ask a Scientist Gaming, we do science questions. So our guest actually writes questions for the audience. Those of you in the theater can't answer it unless you're on Twitch on your handheld or cell phone or whatever it might be. But those of you guys that are on Twitch, you can answer this prediction. And so the question we're going to pop up right now, and I'll put it in chat as well. You can answer via that. But yeah, the prediction is, have we observed more planets or black holes? Exoplanets. Well, I guess we could include our planets in the solar system. It doesn't change the numbers that much. But yeah, the question is, have we observed more black holes or planets? Is there anything you want to add to this question?
Do you have what I said?
I have the answer, yes. But yeah, if you guys are on Twitch, click that predict button on the top of chat and gamble as many internet points as you want. If you're not following, click the follow button. You'll get 300 standard internet units. They're useless for anything outside this channel, but you can use this on channel to request a factoid. You can request we take a drink or whatever, by unlock emotes, whatever it might be. But what do we have more of? Planets or black holes? Or what have we seen more of? Planets or black holes? So you guys have about a minute to answer this question. Were you not sure of the answer?
I forgot what I said.
All right, there's the notes right there, so you can check it out. All right. That's fun, Opie. I will get to yours right after. All right. Yeah, you guys have about 30 seconds left. Have we observed more planets or black holes? Note that you can bet as many of these standard internet units as you want, depending on your degree of confidence in your answer. So let's decide. Have we observed more planets or black holes? What is your answer? You have about 20 seconds left or so. How are you liking Mario Kart?
Oh, it's great.
You were nervous about this, but contrary to comment, somebody should have told David he was mediocre gameplay. All right, 10 seconds left. Get your answers in. Boop. I mean, you're just making your way through all the circuits. Is that the?
Yeah, it's kind of haphazardly.
Yeah. I mean, we're an hour in. You can change to Zelda if you want, or keep playing. It's totally up to you, or whatever game you want.
Well, I'm enjoying this for now.
Before that, we have observed more planets or black holes. David, what is the answer?
We have observed several thousand planets with the Kepler Space Telescope. It did a great job. I think it confirmed 2,000 or 3,000 planets. Oh, that was not the third lap. I don't want to go up that hill either. Sloan Digital Sky Survey observed millions of black holes.
So the answer is black holes.
And now what it observed were things called quasars, but quasars have to be black holes. They can't be anything else. And I have, you can see my YouTube channel. It's YouTube at Dr. Collins. And I have a whole course on extragalactic astrophysics, which is really geared towards people in the class. But I put them online, and they're reasonably good stories. If you want to learn more about that.
I like it. So that was unexpected. Black holes is the winner. Congratulations. If you gambled on black holes, you got a 3.15 to 1 payout on your standard internet unit. So congratulations. People thought it was more planets than black holes. So planets, you mentioned this. There were 2 exoplanets at the time. So in the last, 15 years?
Yeah.
Several thousand. So that's an exponential
Kepler
curve?
was exquisite.
Wow.
It went from laboriously crafting all of the device that you need for every single single planet you found to having a purpose-built satellite that just parked on a field of stars and did nothing but look for planets. Can you blow these guys up? Oh, you can.
Worth a try.
I should have saved it though.
Man, so when you know what you're looking for, it's easier to find. I mean, I love the analogy to this is classic, happens in archaeology all the time, right? When you know what layer and what strata and what location, then all of a sudden you find this plethora of dinosaur bones. Same thing in astrophysics.
Right.
That's pretty fun.
Yeah. Ooh. Yeah, when you unlock a new level, you get to play for a while.
That's perfect. All right, Red the Mumbler wants to know, what's the coolest piece of equipment you've got to use in your career?
That's a pretty fun question. I
mean, it depends how you define use, right? Because you use
that's
web, right? Like web
I wouldn't say that I'm a web user, because I've never written a web proposal.
I see.
So the piece of equipment that I use most are supercomputers. And my favorite supercomputer was called Kraken. And it was, when it was built, it was the fastest academic computer in the world. So that was a really fun machine. When I was in college, I got to work at a particle accelerator, and I was building parts for a particle detector that was like a 4-story building, and that was pretty fun. Recently, I've started working and it's very early on in the development, but I've started a collaboration with the mechanical engineering department. With their supersonic wind tunnel facility, trying to make supersonic turbulence in the lab, because turns out that's really never been done, except for on shock tubes and explosive devices. Nobody's ever really done it in a wind tunnel, so we're going to try to do that, and that's going to be pretty fun. So really, what that project is about is about trying to, so given a cloud of gas, if the flow through it is subsonic, then it doesn't make it any denser, because the density perturbations just get carried away by the sound waves. But if the flow through it is supersonic, then where the flow is supersonic, it'll get denser. And if you're a big cloud of gas in outer space, those density perturbations can get big enough to form stars. And if you're in the lab, that's not possible. But nobody's ever measured really the relationship between how dense it gets and how hard you smack it. So given a certain velocity of the turbulence in the cloud, how dense does that cloud get? Is something we'd really much like to know. So I get to use this supersonic wind tunnel, and that's going to be really fun. And I'm also have a project on this enormous laser in California, which is a 10-story building of laser. And that's a similar, we're asking the same kind of question. If you smack a bit of gas, how dense does it get? But we're doing it with a huge laser. And that project is a little bit further along. So we've actually taken data and fired the laser a couple of times. And that was pretty fun. Half of the data is great and half of the data is terrible.
So we have a follow-up on our prediction. Well, a couple of follow-ups. Matt isn't a Robert thought it was going to be a trick question in regards to the terminology observe. Because you don't observe a black hole, you observe symptoms in the black hole, but I observe enough.
Yeah, we observe symptoms of planets too.
Yeah.
We have only actually observed a couple of planets.
Yeah, that's fair. But man, I'm not going to try to pronounce your first name, but the question is, are there more black holes than planets? Not what we've observed, but actually if you were able to count all of them, which one would be more, black holes or planets? What is your best guess?
Give me a second. There's a right answer here.
Man, well, thank you for the first-time chat. Thank you for joining us for Ask a Scientist Gaming. Put David on the spot.
If every star forms more than one planet, which is a reasonable hypothesis, and only the very most massive stars form black holes, and black holes are only formed through star collapse, then there are more planets than black holes.
All right.
I think that's my answer.
How confident are you in that answer?
I'm like 80%.
80% is not bad.
But we don't know that that's the only way to form black holes. So given that, that we don't actually understand all of the formation channels for black holes, then can I launch on that surfboard? Nope. Then I can't really say with a certainty, but I stand by that. There are probably more planets than black holes. Also, black holes tend to merge. We see a lot of it. We don't know why.
Matt isn't a Robert has asked me to turn down the game volume. I will do that just for Twitch. Turn it up in the house.
That was a
Sorry
bummer
about
time.
that. Man, that's a fun one. That's one of those questions you don't spend time thinking about, but it's something important, right?
Right.
All right. Opie's following up on a previous one. I know you mentioned parallel universes not likely to exist, but considering quantum mechanics explains a multiverse theory, how is that explained in astrophysics, since quantum science has grown so much and taught us even more than what we knew before? So that's the many worlds interpretation of quantum mechanics.
Right. So, I think some of that is, to be frank, beyond my pay grade.
Note that his pay grade for the stream is 0.
That's right. I'm not really an expert on the really subtle details of the local reality versus non-local reality debates around quantum mechanics. But all of those kind of quantum mechanical effects all exist at the quantum level. And it's really unlikely to look anything like a Marvel comic.
I like it.
Yeah.
All right. Manuel wants to know, little sister asked this question, so he's typing it in. Why is Pluto not considered a planet anymore?
Oh, well, because it's the same reason asteroids aren't considered planets. Because when we started looking up in the sky with telescopes, The Mercury, Venus, Mars, Jupiter, Saturn are all real obvious in the sky. And if you just watch the sky a little bit, you can tell they're there. People have known they're there the whole time that there have been people. I just totally burn out. So then when we started finding other things in orbit around the sun, we just called them all planets because that was things that were in orbit around the sun. It took us a long time to realize that the Earth that we live on is going around the sun, and so is Mars, that red dot in the sky, also going around the sun. So that took a long time to figure out. And then once we figured that out, then we realized, okay, well, what else is going around the sun? Let's call it all planet. So everything was a planet. So we found all of these asteroids. Now, I'm calling them asteroids now. We found these other things. And you can tell that they're very small, and they're not round, and there's a lot of them, and there's really a belt of them. There's like a band of little, small, rocky things. They're not planets. Once they said, well, okay, these things are little and really not anything like a planet, then they became not planets again. So for a minute, we had like 6 or 7 planets. Then for a minute, we had like 30 planets. And then we were like, oh, yeah, those things aren't planets. So then we were back to 6 planets or 7 planets.
So if we were to fudge the definition to include Pluto as a planet, how many additional things would we have to?
7 or 8. So you'd have to include Ceres, which is in the asteroid belt, but every bit as much as a planet as Pluto is. Sedna and Haumea and Makemake are all other trans-Neptunian objects that are all pretty much like Pluto, and so all those things are now considered dwarf planets. So it's kind of like if you're classifying 4-legged animals, and you classify them all as dog for a while until you realize that some of them are actually cats. I mean, everybody's going to be happier by calling them the right thing. You're going to understand how to feed them better, where they came from, what they're about. So,
I like it. So what's the formal definition of planet? This is a song that my kids listen to. It has to be spherical. It has to pull in everything around it. It has enough gravitational mass. What else is in that?
Round in the plane and cleared its own orbit, I think.
Okay.
I think round and cleared its own orbit are the important
Those
ones.
are the main ones. George Jettison. Cats are now dwarf dogs. Thank you, George. I like it. Red the Mumbler. Hey, Bulbous wants to know. We heard that Hurricane Milton, when it hit Cat 5, there was a mathematical limit to how strong it can get. Why is that? Oof. Any idea? There's some kind of feedback self-regulatory mechanism where wind balances out like water volume or something. It's something, an energy dissipation mechanism, but...
Yeah, I'm not actually sure. That is a cool question. Oh, man, I should not have hit that thing. I was being greedy and going after this.
That was so forgiving. It pulled you to the end of that.
I know, that was
Not the
pretty nice
start.
of it.
Wow.
I almost shot that thing right back in my face. So that's actually not something that I know.
You're letting down the audience.
I
with
know, right?
Both
Sorry.
your gameplay and your science. It's all going bad, ladies and gentlemen.
It's terrible. But I mean, so there's just as if I'm gonna make something up, which I'm gonna because that's my job here. You know how much water is there? You know how big the storm is and how fast it's feeding on the energy in the water, and you know how long it's going to be there. So you can sort out basically the upper limit of what it's going to be like. There are other feedback mechanisms, as Ken said. So you dump energy in, and then that energy comes out as rain. So there's a relationship there. So I'm not 100% sure.
All right. Opie wants to know, do you think there's possible life on Europa?
Oh, yeah, I hope so.
Well, first, what is Europa?
Europa is a moon of of Jupiter, and it is warmed by tidal crushing from Jupiter and the moons around it. So it has this. It's geologically warm, and has this ocean underneath a crust of ice. And having heat and water is really all we know we can say about what we need for life. So I think it would be pretty neat, and I hope that we're really very careful when we go try to measure it. I also think that Titan might be an exciting place for life. It has a gas that has has an atmosphere that has a surprising amount of methane in it.
So George has a follow-up, and this is our discussion earlier about scalars of time and things like that. How warm is warm? What does warm mean to you? It's now 3 Kelvin in this instance.
Totally context dependent.
Yep.
So the warm interstellar medium is like 10,000 Kelvin, which is pretty hot. 8,000 Kelvin.
So how warm is Europa?
Warm enough for liquid water.
All right.
So
over 0 degrees C, depending on the pressure, I guess.
Right. Yeah. Yes, depending on pressure. So actually, I'm not actually. Because there's that crust of ice.
Yeah, but warm enough, presumably, to support life.
Warm enough to support water. Warm enough to support life if it can. I mean, life. We know that life exists in all kinds of really bizarre places.
All right. Chat, if you guys have questions, put them in there. I promise we'll get to them. I'll copy and paste them into my document. But in the meantime, I'm going to check if anyone in the theater has questions, because we have not been asking.
Oh, yeah.
Anyone have a question? Raise your hand. Nice.
Start playing Zelda.
Oh, yeah, totally.
Quest for Zelda. You want to go Zelda?
Yeah.
Other questions? So much questions or requests. But yeah, use chat. You guys are logged into Twitch. It's way easier to get out. They're sick of your Mario gameplay.
That's okay. Zelda's going to be awesome on this screen. I'm going to play this, which is going to be all blue shell.
All right. Contra wants to know, I'm interested in the extreme violence you mentioned happening, tearing apart near black holes and being extremely bright. Since I don't know what to ask you about that, would you mind expanding? Because I'm curious. So David's falling into a black hole. What do you experience? Why does it generate light?
Right. So it's complex physics that we're understanding better and better as we get exciting telescopes like the Event Horizon Telescope. But basically, it's really easy to get rid of energy. So it's really easy to get smaller, but it's really hard to get rid of spinning. So you always wind up with a disk. So you have a cloud of. Oh, that was stupid. Sorry, I got distracted by blue shells. Okay, so around so nature likes to make disks in outer space. It's a pretty common.
What is this, blue shell mode?
It's all blue shells.
Oh my god.
And so you get this thin pancake of gas that's all orbiting around the black hole. So the black hole gravity is very strong, and so it's pulling on it really hard, and so that makes it spin around like crazy. It also makes the gas very thin, so there's a lot of pressure in. This is so much harder to try to stay in second.
Yeah, I don't know why you're. Yeah, this is pulling your focus more than actual gameplay.
It is. Maybe I'll back that up.
No worries. As long as you're having fun.
Yeah.
Oh, we're switching to Zelda this time?
Yeah, let's. So So all that gas forms this thin pancake that's spinning around really, really fast, and it's being pulled by the black hole really hard. So the pressure in that gas is large, and the gravitational force in that gas is very large, and it's going around incredibly fast because it has to, because that's how you stay up in orbit around the black hole. And all of that rotational energy is hard to get rid of. So things are spinning around really, really fast. And all of that spinning creates a lot of friction. And that friction heats up the gas so that it glows in the X-rays and the ultraviolet. And that's kind of in close to the black hole, but not quite at the event horizon. So the event horizon is the central part where the black hole actually starts. This is several times the radius of the black hole out from that. Let me get the game.
Yep. All right. David's taking a brief break to switch out games. We are going from Mario Kart to Zelda. Which one are you doing? Breath of the Wild or Tears of the Kingdom?
Breath of the Wild.
So that's your go-to. Tears of the Kingdom is the newer one, right?
Yeah, that's right.
Yeah.
And it's a fun game. Oh, how else when I say that? It's a fun game, but I don't know. Have a warm spot for Breath of the Wild.
It's one of the modern classics of gaming.
It really is.
It's a go-to for many. All right, Matt isn't a Robert. That name always gets me. Matt isn't a Robert.
All right.
Are there any theories about the 5/6-sided shape on Jupiter?
Oh yeah, that's pretty well understood. Actually, it's a fluid dynamics property. There's one on Saturn too.
So what is the shape? This is just a cloud mass?
Yeah, so it's a hexagon on the bottom, and it's basically things are going around and going in and out at the same time. So if you think about, this is on the bottom of Jupiter, towards the equatorial pole. So things are spinning around in funny, complicated ways, and also sloshing in and out around the pole. And they happen to be sloshing in and out and going around at a 5-to-6 ratio, and that happens to be what nature finds energetically favorable for that. So, yeah, it's a really boring answer. It's just kind of fluid dynamics is weird sometimes.
Yeah.
Especially when you're spinning and huge and made out of gas that's very tall.
I was really hoping the answer was aliens there. But
I know, right?
You let down the whole audience. All right. Red the Mumbler wants to know, what's your favorite sci-fi movie and why?
Favorite sci-fi
Doesn't have to be astrophysics related. Just general genre of sci-fi. What's your favorite?
I'm gonna go with Time Bandits because it's really stupid, but also really brilliant. So Time Bandits is this really weird movie about a band of short people who steal a map of the universe from God and use it to go steal treasure. And they steal from Napoleon, and they steal from all kinds of people. And it's deeply hilarious if you're 12.
Or David Collins.
Or me, and it's always been funny.
That's awesome.
So I would say that's probably my favorite sci-fi movie. If you broadly classifying sci-fi movies.
All right, so that leads to one of my favorite questions we ask every guest on stream is there's movies you watch that you're like, oh, they got everything I know in the universe wrong. So what movie or TV show gets your discipline right and what gets it wrong?
Whenever you have to travel faster than light, you get it wrong. So one thing I enjoyed about The Martian. Take my hammer.
Wow.
So The Martian.
Ultra violence. We're back.
I know. So The Martian was really good about actual space travel because it really dealt with the orbital dynamics of getting a rocket to Mars. How do you actually do that? You have to deal with the fact that you're going around the sun at the same time. And so that book really got that right. And that was really enjoyable. Mm-hmm. Most things treat space battle like a naval battle, and it would look nothing like that. because you're always going to be in orbit around something, and that changes the dynamics. So, for instance, so anyway, that's a longer tirade. So anytime there's a dogfight in space, that's nonsense. It would never look like that. There you go.
So I mean, so you're watching something like Star Trek, and obviously to visit other planets, they have to go faster than light, which breaks physics. I mean, you as a physicist, how hard is it for you to disconnect and just accept that one axiom exists because of warp drive or whatever technological widget makes that possible?
Oh, I died. So generally, as long as they don't try too hard to explain it, then I'm pretty okay with it, because you just have to if you're going to have a good story.
Yeah.
Or if there's a funny story around it. So that's actually good. And there really aren't very many of those. So I really like, the warp drive in Star Trek is designed around moving the space. So moving faster than the speed of light is actually not a problem. It's passing photons that's the problem. You can't locally pass a photon, but nothing says that two things can't move apart faster than the speed of light. So there are galaxies that we can see that are moving away from us faster than the speed of light. So the Star Trek convention is that there's a bubble of warp around it, and that moves the space and not the particles. So I love that. That actually works. And that's the only one that I think actually makes any actual physical sense.
That's awesome.
Everything else is kind of fun stories. But it's pretty easy. Like you have to get around that. So it's as long as there's a good story. And really, like, Ursula K. Le Guin invented the Ansible in the 70s, and we can all just use that.
So Contra has a follow-up. Wait, what? How do we see them if they're moving away faster than the speed of light?
Because the photons just get stretched out, and they just get stretched out twice as much as their original wavelength.
So for the general viewership, what does a stretched out photon mean?
That's a great question. So a photon only has one property. It's its wavelength. And there are two ways to make photons appear longer. One is, so kind of like if you ever hear a car go past you and the pitch drops, that's called the Doppler shift. And the Doppler shift is because the sound waves or the photons are being produced, and then the source is moving away from the wave it just made. So the waves are effectively a little bit longer than they would be if you were just sitting still with the car. The other thing that happens is the actual space stretches out in outer space, and it stretches out as things move through space. They get stretched out just because the space is stretching out.
All right, catching up on a few. Sarah wants to know, how far are you in the Breath of the Wild?
In this game, in my other game, I completed it and I got all the Koroks and finished everything. In this one, I have not beaten it yet, so it doesn't tell me a percentage, but I've only unlocked two towers. I got the tower on the Great Plateau and the tower in this region. And I'm going after this tower that's right here, and I keep messing this up.
Did you see the bow / flight glitch in this, where you can shoot yourself super fast across the map? It's speedrun strategy, actually.
Oh, that's really
you do
fun.
the right sequence of events, and you can just projectile yourself across the level. It's pretty amazing.
Hilarious.
I think it's in this one, Breath of the Wild, but check it out.
There was a
YouTube
lot
video.
of fun glitches in this one. It's really fun.
Yeah, I love it. The more complex the game, the more intricate game-breaking glitches will be. But
yeah,
all right.
That's one thing that's really fun about Tears of the Kingdom. It's fun to glitch, but also I think because of that, it's not as tight a game.
Yeah, that's fair. All right, Red the Mumbler has information for you. There's a new Time Bandits show, but he doesn't know if it's any good, or they don't know if it's any good.
Really?
Yeah.
Did what's his name do it? I mean, of course, nobody else would do it.
I don't know, Red, if you have any follow-up information.
Terry Gilliam?
That's fun. All right, let me catch up. What do you have to say to people who don't think there's anything left to discover in space and don't see the importance of space exploration?
Well, that's very boring.
That's your answer.
That's my first answer. I mean, there's always things to discover, and every time we discover something in outer space that's of significance, it revolutionizes our understanding. And our understanding of dark matter and dark energy is going to unlock so much. So when we understood thermodynamics is really boring. It's about why gas gets hot when you squeeze it. But once we understood that, then we could understand air conditioners. And air conditioners not boring. They make the summer not suck. So there's a lot of really seemingly dumb, pointless things that you can do that actually have a lot of really great benefit. Once you really properly understand it. I gotta stop doing that, man. So I'm used to playing on this ultra buffed character that has, all of the good armor and is really strong. And I forget that those guys are actually still hard for this character.
You're just getting wrecked.
And I'm just getting my butt handed in.
I like it.
Let's try that again.
Living up to the mediocre gameplay on
That's
this
right.
one.
Pretty M and mediocre.
I like it. All right. Another question. Red the Mumbler. Bulbous wants to know, can you land on a gas planet?
No, you'd be crushed. Was that? There's really never a solid. So the core. Are you guys here?
Yeah.
Oh, what it is, guys? I know you were in the room. So the core of Jupiter is metallic hydrogen, and that's like really solid. But it's like so solid we don't even that's not even solid. Like that's bizarre, whatever that is. And the transition from the actually very solid metallic hydrogen and the just merely high density gas is going to be something that's weird. So you would just get crushed on the way down. But it does rain diamonds because of that crazy high pressure. I saw a really cool talk. I went to a conference in the spring on high energy density laboratory astrophysics, which is basically blowing stuff up to do astrophysics. It's super fun. And one of the things that the people do with these huge lasers is try to create the gigantic pressures that exist in the center of gas giants like Saturn. And the pressure's high enough to create diamond. And there's a lot of lightning and methane, so there's all the right sources. So there's probably a fine rain of diamond in the center of most of the gas giants.
So Cuddle Puppy has a related science/political question. How easy will it be to colonize Mars/Titan? And what other excuses can we give to billionaires so they don't have to try to fix things on Earth? Raining diamonds?
Yeah. Well, I think it'll be pretty straightforward. Water is the big problem. Okay. I'm gonna save.
Clever.
This is the fourth time I've gotten this. What?
Oh, nice. Veteran.
I just need to get away from these guys a little bit. These choo-choo jellies are really cramping my style. Okay. What was the question?
What excuses can we give billionaires so they don't have to fix things on Earth?
Yeah. I don't know. I think they should fix things on Earth. But yeah, I think that colonizing the moon is. I think that actual colonies on the moon and Mars of like actual substantial amounts of people are going to be limited by how much water we can actually find there. Oh my God, I know how to play this game. Jesus Christ.
You're right. You're
There you
focusing
go.
more on this than Mario Kart.
Yeah, I know.
That was unexpected.
I know, right? This I thought was going to be pretty straightforward, but I think because of the fact that I've now totally cocked it up 4 times.
Now there's pressure to perform. I get it.
Well, I saved so I can do some of it again.
Mediocre gameplay.
Mediocre
Expert
gameplay at
science.
its finest.
You're nailing it.
Okay, where were we with questions?
Man, we're talking about tricking billionaires into colonizing Mars and Titan.
So I mean, everything needs water, and we need water for everything. So however much water we can actually find on Mars and the Moon is going to dictate how many people it can actually. Where'd he go?
Yeah, I love the discussions about harnessing water from rocks. Right?
Yeah.
Because if there's hydrogen and oxygen, if you can extract those and put them together, that is water.
Right.
Should be fun. That's some science fiction right now. We don't have good ways to do that.
That's right. But it would be cool.
I agree. All right. Stag wants to know, Eureka moments or really surprising findings in science are few and far between, but are increasingly gratifying when they happen. Absolutely. What is a Eureka moment that you've had in your career?
Well, understanding that, there you go. Okay. Okay, sorry. Eureka moments in my career. So probably,
GG's, by the way.
thank you.
Did it.
Now I got there. Is there any more drop that I missed? Oh, some guts. Okay, now I'm going to save. There you go. Okay. Well, so my most recent Eureka-ish moment, I haven't actually been able to make. Did I do that? I haven't actually gotten it to work yet, but if I do, it's going to be really dope. I realized. So one of the projects that I have is on this huge laser, and with this huge laser, we're blowing the snot out of this little piece of plastic to look at the shock waves that are built up in it. And I realized that so there's a couple of things that are hard about this experiment.